Hello everyone, and welcome back to a new episode of Advent of Code. In the last episode, were most of the way through episode 5 when, not episode 5, but rather puzzle number 5, day number 5, millisecond number 5, when we ran into some performance issues that A, made our program run really slowly, and B, actually run out of memory before it could complete. So I said I was going to look into that off camera, and I did. And it didn't take as long as I expected. We maybe could have done this on camera, but there were two main things that we did. So first, I don't care about this anymore. First is the thing that I think did do on camera is I made all of these things strict because I sort of suspected that their being lazy was causing us to build up a bunch of deferred work when we're going to need the work anyway, so why be lazy about it? Let's just make it strict. And the other thing that I did was run. So we've been running our programs via runghc, which is basically like the interpreter for Haskell. GHC is the glorious Glasgow Haskell compiler. I don't know. It's the Glasgow Haskell compiler, but there's some joke about the G being glorious. I don't totally get it, but and so that's fine. But interpreters are kind of slow, and we were running into we wish it had been faster. So what I really should be doing is compiling the program and then running the executable. And in particular, wait, how do I make you guys look at this again? Here we go. In particular, I said stack GHC. Oh, O2 is invalid. I see. --O2. So optimization level 2, which is the highest level of optimization GHC will do, produce me a main file. And then I ran that on my just part 2, and it produced an answer in 23 seconds, way better than the several minutes we had been waiting. And the answer is in fact hundreds or thousands of times larger than our original answer, which explains why it was taking so much longer. And I went back and ran the program again with optimization against part... I think I ran it against just part 1? I'm not sure. Maybe I never did. Yeah, originally part 1 with runghc was taking 2 minutes. But with compiled, parts 1 and 2, where 2 is 100 times slower, finished in 7 seconds. So okay. If we're having any performance issues at all, we should really try turning on optimizations. They help a lot. And then you see me doing some fiddling around here with sleep and echo test. This is because I was configuring tmux and I needed to test this, so I'll show you. So let's say we're running some program that's going to take a while and we want to look at the source file for a while. Oh, look at that in the bottom. Our bash, what is it called? Window? I guess our bash window has lit up and I can go look at it and say, oh, something happened here. Great. So now we get notifications about something happening in a window that's not the one that we're looking at. Anyway, we don't really want that committed here. Okay, great. And so I already explained how this program worked. If you're just getting here, for some reason chose to start on day 4, or episode 4, and you're very puzzled by this program, that makes sense. I sympathize with those feelings, and if you would like to learn more, please go back 1 episode and watch days 3 through 5 in episode 3. I should also, by the way, git add... Why? Oh, I didn't commit day 5 part 2. There we go. And this is in fact all of part 2, right? Yeah. Yeah. Okay. Cool. So with that, on to day 6. Day 6, memory reallocation. A debugger program here is having an issue. It's trying to repair an infinite... sorry, not an infinite... What? I skipped to the next line. Trying to repair a memory reallocation routine, but it keeps getting stuck in an infinite loop. In this area, there are 16 memory banks. Each memory bank can hold any number of blocks. The goal of the reallocation routine is to balance the blocks between the memory banks. The reallocation routine operates in cycles. In each cycle, it finds the memory bank with the most blocks, ties one by the lowest numbered memory bank, and redistributes those blocks around among the banks. To do this, it removes all of the blocks from the selected bank, then moves to the next memory bank and inserts one of the blocks. It continues doing this until it runs out of blocks. If it reaches the last memory block, it wraps around to the first one. So the first question that I had when I read this was, do we put blocks into the memory bank we were taking them all out of? And it turns out in the examples, the answer is yes. The debugger would like to know how many redistributions can be done, that is, how many times we can repeat this deterministic process, before a blocks in bank configuration is produced that has been seen before. So we basically have a state that we're looking at, and wow, I just completely lost my train of thought. We have a state that we're looking at and a function to produce a new state from a previous state, and we wish to iterate this process until we see a repetition of states, and count how many tries that took. So that seems simple enough. And they give us an example here. You start with 0, 2, and 7. The largest one is 7, so we take all 7 blocks out of it and put one here, 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 like that. That's 7, right? Yeah. Yes, the fourth, first, and second banks get 2 blocks each, and the third bank gets 1 back. And so we just do this shuffling around of things until we see a situation we have encountered before. So what is our puzzle input, please? I wonder why it's separated by tabs instead of lines this time. Weird. Okay, well, whatever, I guess. So let's see, bring you guys back over here. And we should not need any fancy business, I think, for this puzzle. We could perhaps, it seems to me, make use of the zipper that we invented in the last episode to sort of walk through the list cheaply. But I don't think that is necessarily the most efficient way of doing it. I think that given a memory bank as a list and an index of a thing that we want to make large, that we want to redistribute, I think that we can write a function that we could map over the list by index, so that would compute how much to change the value by. And so we wouldn't need to do it one at a time. You can do it with just like a little bit of modular arithmetic, I think. So I guess let's get cracking, right? Day 06, source, main. Here we go. Main is going to be interact of, you guys have seen this all before, of course, map read dot words dot lines. Compose this with part 1 and compose that with show, probably something like this. So we read each line, and for each line we map words and map read over the results. We've seen this many times as a way to read tab separated lists of numbers. And in fact, we really should have only one line. So let's just say head, give me the first item in the list of lines of the input. And we'll just remove this map, and we'll just say call words on the line that came in, map read over the list of words. And so part one will just take a list of ints. I keep hitting, like, I don't even know, some weirdo button that is making it prompt me for bad things. Oh, I can ask. What buttons have I been hitting recently? Control H, capital I? How on earth have I been typing that? All right, well, okay, I guess. So anyway, it takes a list of int and produces as output an int. How does it operate? So we probably will want to say part one. We're going to want to use some kind of helper function that is going to track a few more things, like specifically the list of all previous states we have ever seen. So part one of banks, let's say, equals go of banks. Now we could instead write something like part one equals go.return or something, be a little bit fancier, but I don't really see that being worth being clearer to read at all. So in fact, you know what would be nice is to have a I'm thinking of a more generic helper function that we could write, which we could use in part one. So okay, let's try this. Iterations is going to be a function which takes as input an a, well, let's say a function from a to a, and an a, and produces a list of a's? Is that all? Well, that's just iterate, right? But I don't know that that's really what I want. I want something slightly different from iterate that puts the new values at the front of the list rather than at the end to simplify things. Yeah, and I don't ever really want an infinite list back. So I think this feels a little bit like this is what I want to do, is return a list of A's. And it makes me a little bit uneasy because I don't think this is really the right way to do it. But it's the approach that I'm thinking of, and it seems like it ought to work. We're basically going to produce a list of all of the lists of iterations that you could do, increasing in size. Normally, when you want to make a list that increases in size, you just use an ordinary friggin' list and you scan it from left to right. But we kind of want to scan our list from right to left, and so we kind of want an infinite list of the finite prefixes of that infinite list or something like that, right? So I don't know. This seems like it should work anyway. So iterations of f and x equals go of x, I guess, where go cur cons to previous equals a thing? Equals what? Well, let's say all as. So this at here means we're destructuring or pattern matching the value this function argument into a pair of the first element and the last element, like with that's what this does, ignoring the at. We destructure it into a pair of the first element and the remaining elements. But also, please keep a reference to the original unbroken list. So I'm thinking that this is something. So what is our go function returning? It's returning I guess we want something. Oh my god, I don't know what I'm doing. It's kind of awkward, I think, for me to have like the list of things as like both an input argument and sort of the output. But I think that this is fine. We just sort of want all, which is our current and previous. Yeah, okay. So we want all const onto the result of go on f cur const to all. So the idea is to recursively. Does this type check at all, by the way? Not in scope. Go. Oh, I didn't do this. Let's just make this undefined. Incredibly, it type checks. Okay, so that's good news. It's promising. At each step of producing this list of prefixes of our output, we take the current most recent value, call f on that, and put it at the front of the list and recurse with that. Additionally, we take all the list of all previous states we've had and produce it. So I think that this is like, okay, so let's try. Wait, can't I? Oh, I see. I have to. Okay. I would like to now say iterations suck of 10, and let's 0. Let's take 5 of this. It actually works. That's exactly what I wanted. We start with the initial value, and we produce a series of lists of the states of this thing, but sort of like going backwards, where the newest ones are in the front. Perfect. That's exactly what I wanted. My plan is to use this with some function called like redistribute memory. And we'll get a list, and at each step, we'll sort of get an infinite list of all the memory configurations this thing could ever produce. And every time we look at one of these things, we'll say, look at the first element in the list. Is it present in the rest of the list? If so, it's a duplicate and we can stop. If not, let's examine the next state that we might encounter. So I think that that is going to be a useful building block for our part 1. And in fact, I think that now would be a good time to write a redistribute. Let's call it shuffle. Shuffle doesn't have a type, does it? No. Okay, great. Shuffle is going to be a function from list of int to list of int. I see now. I was listening to someone, I was hanging out in the Clojure IRC channel the other day, must have been like yesterday, in fact, and someone was asking about, like, he was working on Advent of Code and he wanted to find the largest item in a list, but if there is a tie, then the tie is won by the item with the smallest index. And we don't want that the value, we want the index as the result of our function. And so he was clearly working on this puzzle. And I wrote, in response to this question, I wrote a little function to do this in Clojure that was relatively short. It's a little bit less convenient in Haskell because, like, we don't, well, neither Clojure nor Haskell really likes indices of lists because linked lists are not great structures to index. But it should be fine, right? So what exactly is it that we want to do? Okay, well, let's start with another helper, where we say target is a list of int and produces an int. And target is going to take a memory bank and tell us which one should be the victim for redistributing. Or perhaps the beneficiary, who knows whether memory banks like it or not when you take their memory and empty it out. I don't know. So what I would like to do with target is say target of x's equals, yeah, sure, x's is fine, I guess, equals, so we want to compute the maximum of some function across this input, right? Maximum by, I believe, is a thing, right? But I suppose it must be in import data.ord. Maximum by? It might be in data.list, I'm not sure. List. Yes, okay, so data.list does have such a thing. And we also, what is an ordering, please? LT, so these are all in scope for us, okay. Great. Actually, though, we want, like, import data.ord comparing. Comparing. So that, does that type check at all? What is the type of this, please? Hello? Why will you not show me this? Yeah. I mean, fine. So, no instance for ord arising from comparing. It's ambiguous. Yeah, very funny. Okay, I don't really care about that. I just wanted to know what is the type of this thing, please. But since our function doesn't compile, it won't tell us the type. All right, well, we'll ask Google then, I guess. Maximum by, first of all. Yeah, fine. Comparing. There's like another thing near comparing that is what I want. Okay, so down is a way to reverse sort order easily. Okay. Comparing. Is there an index somewhere? There is, look at that. Oh, but I don't want that. That's all of base. comparing down, okay. Okay, maximum by comparison of zip x's with that, sort of, right? So they want like first. Any right parents? Okay. So this compiles fine. Oh, dang it! Here, look, we're doing things. Okay. So what I have done is written sort of a function here, which is not correct entirely, but it's sort of a first step where first I zip the list x's together with the infinite list of integers starting at 0, and then I compute the maximum of that list, where I compare items by looking only at the first part of that tuple, i.e. the value, and having gotten back the tuple of value index that was the largest, according to that metric, I return the second part, i.e. the index. And so this should work for some inputs. Target of, for example, 1, 2, 3, 4, well, 3, like this or whatever. It'll say index 4. Yes, correct. This index here is the largest one, and therefore it is the one that we should do work on. But what if we now wrote this? What do we get? We get 3, i.e. this. So maximum by is evidently right biased, and we wish that it were left biased. But actually, this is just silly, because I don't have to do this comparing first. Tuples already compare in an order where they look at the first and then use the second for a tiebreaker. So I can just say maximum like that. Maybe something like this is actually a nicer way to write it. And now I still get 3. That's no good. Ah, right, because I want to invert the order that the tuples typically sort in. Okay, sure. So what I could do is write map down on this. Saying that I wish to have the second part of the tuple considered in inverse order. And I don't think that this will type check just yet. No. And in fact, right, we now no longer need this nonsense. Just maximum is fine. Yes, and so now the problem is we have a down int when we want an int. So tell me more about down, please. Is there a... Okay. Okay, whatever. We'll just deconstruct this. Equals let down I equals this in I. There, that compiles. And now, when we write this function, we get 2. So what we've done is we've constructed a list of, we've zipped x's together with a list of all the indices of x's. But we've attached a little tiny bit of metadata to those indexes, saying please sort these in reverse order if anyone ever asks you to sort them. Sort of. That's really not at all what has happened, but it's a bit like that. And then we compute the maximum of that list, which results in us choosing the largest item in the original the index of the largest item in the original list. But when there are ties, they will be broken by sorting these weird upside down integers. So, and as a result, we get the target we were looking for. Okay, great. And you know what? We really should return more than just an int. We should return, at least we should return 2 ints, right? 1 saying the index and 2 saying the value we're going to remove. So let's make a tiny little data structure for that, I suppose. Data evac order. Sure. Equals evac of int. But then we still don't get the whole point of giving this a name is that we can use useful names for the function. So we'll use Haskell's record syntax here to give these fields useful names. Evac bank int and size int. And we'll return an evac order from this. And we'll say, instead of calling second here, we will just say let size down index equal in evac index size. Parse error on input comma. Oh, of course. We didn't want a comma there. Okay, so this still compiles, still type checks. Great news. And we still have not written our main function at all, but we're starting with building blocks that look like they'll be useful somehow, and then we'll just sort of assemble them when we find a place to use them. So shuffle, I think, is going to be the hard program hard function, I guess you might say, to write, because I'm hoping to do it all in one pass. So let's see. I guess shuffle of x's will equal let e equal t, target of x's. And I think we'll just destructure it right here. Evac bank. Evac. I see. So it actually was not very useful to give these names at all, because we're using names when we pattern match them anyway. I'm just going to go back to that, actually. Let evac bank size equal target x's. And let's also get, I suppose, len equals length x's. I'm sure we'll need that for something. New size equals I want this to be a function. We'll call it resize. Equals resize we'll give this a name T, I guess. Resize T. Actually, doing this all with this is fine. This is fine. Yeah, in fact, we don't need to give a different name to this. We can just define a function inline as part of this let. Resize of I equal something defined. Yeah, like that. A whole. And I think at this stage we just want to write in map resize over x's. This is my thought. We compute what to evacuate and the length of the list, which we'll want for some reason. And from, actually we want resize will take an index and an amount and produce a value. So we won't just map resize, we'll zip with resize the list of indices of things and x's. Yeah, that looks more promising. So the trick now, of course, is to write a resize function which, given the information about which bank is being evacuated and the index and size of a bank, determines what its new value should be. So there's a few ways to do this. There's a few cases to this. One I think is easy. When I is equal to, no, not easy. Well, yeah, actually pretty easy. When I is equal to bank, then we're basically just taking the size of the old bank and dividing it by the length of the list rounded down, right? So that's size div len. I think that's right. Because we start with the one above it, and only, let's say we have 16 memory banks, right, as we in fact do. If there are exactly 16, then we get one back in the old bank. But for any number smaller than 16, we get 0. I think that's relatively straightforward. And so the other case is otherwise, right? So it's going to be something based on the old amount plus some fraction of of size div len plus something, right? Size div len plus amount plus something? I'm not sure exactly. We start with the old amount. We add at least size div len and possibly 1, I guess, is the idea. Because if there are size div len, yeah, size div len is how many are given out to every program, every memory bank, I should say. But some memory banks get one more than that. Like if we have, say, 17 in the old bank, then the very first one will get 2 and all the rest will get 1. So let's call this leftover, where leftover equals something. it never occurred to me that you could use a guard for like a definition of a value rather than a function, but I think you should be able to, right? Yeah, why not? So, all right, give me a REPL real quick. What is 1 minus 5 mod 3? Mod 3? It's minus 1. Okay, that's more what I wanted. So, of course, 1 minus 5 is minus 4. Yes, math checks out. And if you were to add 3 to that twice, you would get 2. So modular arithmetic works just fine with negative numbers when using mod, which is good to check. I haven't been muted for like an hour, have I? No, that's good. Okay, just gotta double check that every so often or I'm gonna like go crazy. So I think the idea here is to compute the size mod len. That's how many are being distributed as leftovers. And if that number is at least as large as the distance between the two items, then we get 1, otherwise 0. Okay, so I think that's the idea. So when size mod len is greater than or equal to what? The distance between I and bank mod len equals 1, otherwise equals 0? It compiles, it must be right. So let's try a few examples though, just for fun. Shuffle of, and let's grab an example from the test input here. I won't bother showing you guys this list. 0, 2, 7, 0, 0, 2, 7, 0. We get back 2, 4, 1, 2, which is the correct answer. Astounding. If we next shuffle that, we get 3, 1, 2, 3, which is the next correct answer. Unbelievable. So I'm pretty confident with this now. Sort of just like made it all up on the go, but it worked on the first try, which is like, I don't know, wow, okay. So now we just have to write part 1, given all of these useful functions. We have shuffle, which is the thing that takes us from step 0 to step 1, and then step 2, and so on. And we have iterations, which is the thing that says, given a function like shuffle, here's a list of all the inputs you will ever get if you did this forever. And so part 1 just has to basically call like iterations of shuffle on the banks, and then like do something interesting, right? Which is basically what? The length of the Okay, so let's do something. Let's do it backwards, rather than trying to write the expression outside in. Let's try to write it inside out, which is usually easier functionally anyway. Let's let all states be iterations shuffle of banks. So now we have a list of all the states that this thing is ever going to get into. And what we want to do is remove all the states which, here's an idea, another helper function. Unique is a function for any two value, for any type A where A can be compared for equality, a list of A to bool. And unique is like pretty simple. Unique of empty list. We should never get an empty list, but we'll say, in case we do, we'll say true. Not in this example. If unique were a more general function, of course it should test for empty emptiness. Okay, so but unique of x's equals not x elem x's. And I think there's a function called not elem, but it's not like we need it, right? We have not already. So now we have that. We have a way to test whether the items in a list are unique. And we have a list of lists of values, and we want to find the first one that is not unique. So let's try repetitions equal drop while unique of all states. And now repetitions is a list of all of the state lists that have that are not unique. And so we can just take the first one of those okay, so if we get a non-unique list, it'll have at least two items in it, right? The first thing, okay, so how many, after the fifth, the infinite loop is detected after the fifth redistribution cycle. So we started with this, that's state 0. We did a thing 1, did a thing 2, did a thing 3, did a thing 4, did a thing 5. So the fifth time we did a thing, we wound up with 6 different states. Okay, so when our list has 6 states in it, the answer should be 5. So we should subtract 1 from length of head of repetitions minus 1. Okay, this still compiles. Sorry. Why don't you guys have a look at this code? What do you think? Length of head of repetitions minus 1. I'll get the hang of this someday. Did I already get my input? I didn't. Okay. Wait, but I did though, right? I remember doing it. Where did I put it? I guess I copied it but didn't paste it anywhere? That doesn't sound right. Huh. Alright, I guess that's what I did. Day 6, input.text. There we go. Oh my gosh. It didn't copy the tabs. Or Emacs replaced them. Okay, so we need to go to the other shell here. Cat input.text. I have an Emacs set to like never put tabs in my files. And so in this case, I wanted some tabs. So I need to use something other than Emacs. Like, of course, I could, temporarily reconfigure it or something, but yes, actually, just reread, and now there's tabs, so this will all look fine. Okay. So here's our list of memory banks. How could we test? Get out of here. How could we test this on something a little bit smaller? What if I were to just say stack run GHC, but I will echo to you a different input to use. And we'll just use their test input, 0270. 0270, type to this. Yeah, should stack run GHC of source. There we go. 5. Hey, that's the right answer. Great. All right. Well, could be luck, of course, but there we go. And if this starts running atrociously slowly, we will realize we should have compiled. But okay, a fine answer. Got it faster than we could have, like, typed in please compile. So that's the right answer. Stupendous. So what do we do next? Out of curiosity, the debugger would also like to know the size of the loop. Starting from a state that has already been seen, how many block redistribution cycles must be performed before that same state is seen again? Sure. So this is pretty straightforward to add, I think. But before we do that, important stuff. Day 6, part 1. It just feels like, I don't know. I got in the habit of using Git for everything, and even if I'm not pushing it to a remote server, although actually I should. You know what? Forget it. We'll do that off camera. Of course, the passphrase wouldn't show up on camera, but you guys might hear what letters I'm typing. Spooky. I don't know. It doesn't matter. But, okay. So, anyway, even if I'm not pushing to a remote server, like having a Git history locally is so nice. I can look at what I've been up to, and just like having a coherent story for the program I've been writing is very comforting. So I'm just in the habit, gotta put things in Git. Anyway, so great. We did part 1. And we correctly added just 2 files, the input and this thing we were doing. And of course we want control.arrow. I should just like put this in all of my files before I start editing them, really. Okay. So this is kind of nice. I actually can just call this solve, takes a list of int and returns what exactly? A list of int. Yeah, yeah, that's right. So a list of all of the states that we had to go through to get a repetition. And we'll just return, that value. And really, like, this is just silly, right? We should inline this as well. Drop while uniques. And we can ADA reduce this banks here as well and just say solve is drop while unique iterations shuffle. So first we compute all the iterations, we drop all the ones that are unique. And we return the first one that is not unique. So now part 1 can inspect that and say how many items are there, -1. Part 1 is a list of, I guess, we'll put a solve in here, is a list of int to int. Part 1 equals part 1, okay, sure, is compute the length of the list and subtract 1 from it. We could write, you know, -1 or something, but pred is a function which, given anything countable or enumerable, returns the item before. So for numbers, that's 1. For integers, that's 1 minus. So this is fine. And it still compiles, which is great news. And just for fun, let's run it again. And get started on part 2. By the way, it returns 14,029. Is that what it was before? I didn't even look at the number before. It was though, 14,029. Okay. Okay, so part 2 is a different function of lists like this, right? And what does part 2 do? So part 2 of x, which is the repeating state, and x's is going to be, so x is the state that repeated, and x's is all the list of states that came before it. And so we can just scan through that list of previous states until we find one that is the same as x, and count how long it took to do that. Which is, let's see. Seen again after 4 cycles, so one, two, three. So they mean after 4 transitions, you get back to the same thing. So if the very first item in x's were also x, i.e. we had a cycle of size like 1, the value we should output would be 1, right? So I think what we're going to do is write 1 plus length of drop while not equal x, x's. So go through the list of x's, throwing away items that aren't x. Whoops, take while, not drop while, this time. Yeah. So count all the items in the input list until the first one that is the same as x, and add 1 to that length. And I think that gets us where we want to be, right? Still compiles. How do I switch windows? There we go. $2,765. Sure, that sounds plausible to me. It's smaller than the first number, right? So there you go. And let's type it in here. It's the right answer. Great. So that was an example of what I was mentioning, I think, in the last episode, or maybe this one, where, like, you know, the Haskell program compiled and it worked. I don't know. It may, like, you would maybe argue that, like, there are a lot of calculations here that could have been type correct but still wrong, and I am with you on that. Likewise here, all of these off by 1 errors that I predicted ahead of time, and, like, still, it's always nice when something works on the first try, right? So let's, day 6, part 2. Nice and simple. And how are we for time? Good Lord, an hour, really? How much have I done today? It was just day 6, right? It wasn't that hard, I thought. What did I spend all this time on? Huh. Well, I guess we're not doing another one in this episode, huh? Okay, well. But as you can see from the Advent calendar, we're close to being caught up. Day 7 has only been out for an hour, and we haven't done it yet, of course, but we're now caught up, and I could start doing this one like on the same day everyone else is doing it now, so that's nice. Anyway, stop talking, end the episode. How about that? Thanks for watching, and I'll see you next time.